get started. It's my great pleasure to introduce Romain Vasseur from UMass Amherst. Romain did his PhD in Paris and Saclay before doing a postdoc at Berkeley and then starting his faculty position at Amherst. Romain has worked on a number of very diverse topics in condensed matter, ranging from from integrability to statistical mechanics and field theories, to many-body localization, quantum dynamics, and more recently, lots of work on more information theoretic approaches to quantum dynamics, including measurement-induced phase transitions. He's also giving the QFarm seminar tomorrow, but today he's going to be telling us about hydrodynamics in low-dimensional quantum systems. And he's won many different early career awards, ranging from the Sloan Fellowship to the DOE Early Career Award, the Air Force Young Investigator Award. So he's one of the bright young stars in this field, and we're very happy to have him here today.
Okay. Thanks a lot, Vedika, for this very nice introduction, and thanks for inviting me here. Today I want to tell you about a topic that's pretty close to my heart and that I started working on a few years ago, so it's relatively recent for me, and which has to do with applying techniques and ideas of hydrodynamics to many-body quantum systems. Okay, and so largely in this talk, I'll try to explain what I mean precisely by this, and hopefully convey that this is kind of an exciting framework, and tell you about a few surprises we encountered along the way. So let me start by putting this talk in kind of a broader context. So most of the research that I do in my group has to do with non-equilibrium quantum dynamics. Okay? And really this is largely motivated by the advent of all those amazing experimental platforms that can be very different, but they have in common that they can be very well isolated from the environment, and they allow some unprecedented control over the interactions, both in space and in time. And they raise many fundamental, questions. And, the very questions that you ask about those platforms can be completely different from what you would typically ask in many-body physics in thermal equilibrium. So in traditional solid-state or condensed matter physics, maybe a cartoon of what you would think about would be this on the left, where you have a system that's coupled to some bath. It's in thermal equilibrium, and if you're interested in quantum physics like I am, typically you would want to go to very low temperatures. So in contrast, for many of those platforms, some of the natural setups are like summarized by this cartoon on the right, where you have your system, so it could be a bunch of qubits or other degrees of freedom that you can prepare in some state. And then you have some type of unitary evolution, and for me, I'll have some Hamiltonian, some interactions that you control, and at the end of the day, you just measure the state of your system, and you would repeat this many times. Okay? And so this is a widely different mindset, if you want. There's no temperature, there's no thermal equilibrium. All there is to it is some initial state, and if you want, solving the Schrödinger equation, right? And so in a nutshell, this is what quantum dynamics is about, and at least today, I won't really have quantum circuits or anything like this. I will have nice Hamiltonians, and this evolution will be unitary. Okay. So broadly speaking, again, the general question we're trying to tackle and understand is initializing the system in some initial state and ask about its dynamics, okay, in a very general setting. So what do we expect? So one of the guiding principles is known as thermalization. And so let me kind of briefly go through what this is about. So throughout this talk, I will focus on an isolated quantum system. So I have some quantum system that I like, say it's a bunch of quantum spins, but it could be something else. And I prepare them, like say, I'm showing them in 1D here, and I prepare them in some product state that I can control, that I know, and so that this is my initial state, okay? And then I have some type of quantum evolution, okay? And so all I mean by this is like, I'm just solving the Schrödinger equation. I have some Hamiltonian evolution with some interactions that I know as well. And I ask about it, what happens under this dynamics. So what you expect to happen very generically is that the system will locally equilibrate and thermalize, okay? And by this, I mean that locally it will be described by an equilibrium state. So for example, it may have like a local temperature coming from the fact that you had conserved energy. So this step is known as thermalization, and you can think of it as like the system acting as its own heat bath. And this is a fairly non-trivial process, and that's not what I'm going to talk about today. Okay, so it's non-trivial because quantum dynamics, quantum mechanics is unitary. You don't lose any information, right? So somehow the whole information of this initial state is still encoded in that state after time t. But if you only focus on local physical observables that you can measure, then that memory of the initial state is gone. And this is what you need for statistical physics to occur, right? And so the only thing that you remember are like conserved quantities, like energy, for example. Okay? And so this is saying that if you measure anything that's like local, the only thing that you can know about is maybe some local temperature or energy density in your system. And any other type of memory of your initial state is kind of scrambled into highly non-local degrees of freedom that you cannot measure locally. So this is non-trivial, but that temperature, could be, so there's some effective temperature if you want in your system, even though there's no equilibrium to begin with. And that temperature profile in general can be inhomogeneous. Okay, so this is just reflecting the fact that that initial state may have, for example, some higher energy density on the left than on the right. Okay, and so naturally the effective temperature may be larger on the left than on the right after that local thermalization step. Okay, yeah, of course, please interrupt me if there's any question. Okay, and so this is not the end of the story, even when you reach that step. So this step is very quantum, it's really, and you expect this to be fairly quick. Okay, so it's kind of a local equilibration step. But of course, that's not the end of the day. Once you have like a temperature profile like this, you expect that your system will still evolve from local equilibrium to global equilibrium. So if you want, it's just saying like, you expect to have energy currents flowing through your system, and and that temperature profile will want to be uniform somewhere. And this evolution from local to global equilibrium is described by the theory of hydrodynamics. When you hear the word hydrodynamics, you probably have in mind fluid dynamics, right? And you probably have in mind, if you took a class in undergrad or graduate school on fluid dynamics, you heard about, you learn about those equations. Euler or Navier-Stokes equations applied to classical fluids and gases. It's a very beautiful field, and you have like a handful of very simple partial differential equations that can describe the very, very complex behavior of, again, classical fluids or gases, right? But something that is usually not emphasized, at least it wasn't for me, is that the theory of hydrodynamics is something a lot broader than classical fluids. And it's something it's a theory that can really be applied to basically any type of many-body system that you may have in nature, and not necessarily just classical fluids. Okay. So what are the key ingredients? So let me kind of summarize what hydrodynamics is all about. So the basic idea is that there's a two-step process in the dynamics that I highlighted in the first slide, where you have like fast degrees of freedom in your system that will relax quickly, and then you have slow modes. And those slow modes will typically, at least in this talk, will be conserved quantities in your system. Okay. And so you have conserved quantities and conservation laws that will play a special role in the dynamics. So for example, in a classical fluids, you will have like conservation of energy, conservation of momentum, conservation of particle number or charges. And those conservation laws play a special role, and that's actually why you have like a handful of equations, in classical fluids. And so for each conservation law, you can write like a continuity equation, right? And so you'll have some current, you have some charges. And so typically those equations will be, so that's an exact, for quantum mechanics, this would be an exact operator statement. But on top of it, so the basic assumption of hydrodynamics is once you assume that, all the fast degrees of freedom have relaxed, the system is in local equilibrium, and once that happens, you can express the current in terms of the charges themselves. So charges of those Qn, they're like the local, the local charges, the local conserved quantities of your system. And so this dependence of the currents on the charges they're known as constitutive relations. And generically, it's something that's expressed as a gradient expansion. So, for example, you could have that your current is directly proportional to the charges in your system. And so if you stop there, this is known as Euler scale hydrodynamics. So if you know the Euler equation of like classical fluids, this would be expressed in terms of those terms. So a typical example would be like if you have a net momentum in your system, you would have a particle current. Okay? So if you have momentum, you have a current. And so different values of different charges would give you different currents. And so physically, those terms will give you ballistic transport. So you can kind of see this by looking at like this one time derivative here and one space derivative there. And so this would describe sound modes, for example. But in many cases, like this term might be zero, and in any case, even if it's non-zero, you may want to include also like contribution of your current, which may be proportional to gradient of your charges. Okay, and so, and in principle, you can keep going in that expansion. Okay, and so this gives rise to Navier-Stokes hydrodynamics or equations, and physical phenomena that you might be familiar with, of course, would be diffusion or viscosity, and they come from those terms. Okay, so even when you write a simple diffusion equation, if you have a single conserved quantity and you write down like a Fick's law or Fourier's law, right? In some way, this is the simplest theory of hydrodynamics. You have one conserved charge, and you write down that your current is just proportional to the gradient of the charge. Okay. So notice that I have made no assumption about my system here. This is completely general. Your system could be classical, it could be quantum, it could be weakly interacting, it could be very strongly interacting. So in fact, hydrodynamics is one of the handful of theories that we have that prefers strongly interacting matter, right? And so the nice thing is this expansion, like those coefficients we can compute from equilibrium. So this is something you compute from thermodynamics. Those diffusion constants are a bit more complicated, but you can also compute them. And once you have access to this, you plug that current here, and that gives you a set of partial differential equations, which you can solve either analytically or numerically, like Navier-Stokes equation for fluids. Okay? And solving those equations may be hard analytically, but numerically, of course, it's a huge, it's a huge speed up compared to solving, like, say, a Schrödinger equation. And I would argue that like the theory of hydrodynamics in some ways the theory of everything. And it's of course like a very old theory, especially when applied to classical fluids. But you may have heard of hydrodynamics in very different contexts in physics recently, from like the quark-gluon plasma and string theory, in ultracold atoms. What I'm going to tell you about is most closely related to this. And you may also have heard of hydrodynamic electron flows, so the fact that some materials and solids, in some very clean materials, you can have electrons that behave like a Navier-Stokes equation, where like the dominant relaxation mechanism is electron-electron interactions, and momentum is almost conserved. Okay. All right, and so in this talk, I will kind of illustrate two relatively modern aspects of this theory of hydrodynamics. I will first briefly tell you about how you can apply this theory to a variety of systems, especially systems even in 1D that can have many conservation laws and not just a handful, and that it still works fine. And in the process, I'll tell you about a kind of a surprise that came along the way, and there was a nice interplay between theory and experiments there. It has to do with so-called KPZ fluctuations in quantum spin chains. But before I go there, maybe let me take a quick break and see if there's any question about just a general introduction. Yes?
In general, how do you know you can separate your time scales like this? How do you know you have these fast ones at max and then slow ones?
Yeah, that's a very good question. So there's kind of a general assumption that this is basically one of the assumptions of the theory. And there's actually not a, one of the assumptions of the theory is that there's an actual time scale where maybe you locally thermalize first, quickly, maybe exponentially, and then you can apply hydrodynamics. But in practice, it's actually known that it's more complicated. There's probably not an exponential approach. You probably have like power laws and things like this. So there's no like clear time scale separation. So it's actually still an open question, I would say, at least to me it is, of exactly where you can stop and like apply hydrodynamics. But in practice, I can just, our experience is that it works well. if you just assume that you will thermalize quickly and then you can apply hydrodynamics. But that local thermalization timescale may not be super well defined in most physical cases. Okay. All right. So let me first give you mention one application of hydrodynamics which is recent and which has to do with thinking of applying this theory in a regime where you might think it may do very poorly, and that is in one-dimensional quantum systems. So one of the messages of this talk will be that 1D is special, and this may not be a surprise to many of you. It's kind of well known that one-dimensional physics can be very unique. And for example, in thermal equilibrium, we know we don't have Fermi liquids, we have Luttinger liquids. You may have heard of many-body localization, which we also think is maybe special in 1D. Even in this context of hydrodynamics, we know that something special happens in 1D. So the Navier-Stokes equations, you can think are sort of a mean field description. And in 1D, you're below the upper critical dimension, and you need to take into account fluctuations. So that is to say, if you have even a classical fluid in 1D, you cannot just naively apply Navier-Stokes equations. So it's kind of all of this is well known. So it's kind of well appreciated that you have a lot of interesting things that can happen in 1D. So another thing that's special in 1D, and I would argue it's especially true for quantum systems, is you have special points, which you have special systems which may have a lot of conservation laws, okay? And they're called integrable points. And so you may have special Hamiltonians which have an extensive number of conservation laws. So what do I mean by this? Instead of just having your fluid that may have conserved energy or particle number or momentum, you may have some special Hamiltonians for which you have infinitely many of those conservation laws. And the existence of those special points has been known for a very long time, so there's nothing new here. One thing that is always also well known is that those points are very fine-tuned in 1D. So that is to say, if you add a perturbation, you'll kind of lose all those extra conservation laws, okay? So of course, that seems like a very good reason to just ignore this altogether, because it sounds like fine-tuned behavior. You could argue that in real life, you will always have some perturbations that will maybe break this special feature. But one thing that I will hopefully convince you of during this talk, and I'll show you a lot of examples, is in some way it's, this behavior is hard to avoid in one dimension. So what do I mean by this? That you always end up being at least close. There are so many of those points in one dimension that it's kind of hard to avoid. And in many cases, they dominate the physics, especially for dynamics. Okay, so if you think of dynamics in one dimension, they're very hard to avoid. And there are many real systems that are close to those special points. And it's been known for a while, and I'll give you a lot of examples. I'm quoting a few experiments here, but I'll give you more detailed examples later. Okay. One last thing I should say is that those systems, they're kind of special. They have some exact solutions in some way, but not in a way that's very useful for dynamics. Okay. So let me just give you examples of systems that are close to integrability in actual experiments. So a typical one is just a 1D interacting Bose gas. Okay. So if you take a Bose gas in 1D with contact interactions, this model is naturally of that class where it has all those conserved quantities. And again, it's been sort of known at least for a while that this matters for the dynamics of the systems. And so there's one of the seminal experiments is called the quantum Newton's cradle. That was from David Weiss' group. And what you're seeing here, this is time, this is space, and what you're seeing are clouds of bosons and some harmonic traps kind of bouncing off each other and not really relaxing on the scale of the experiment. And that behavior was associated with this kind of special feature. This system is not thermalizing, at least on the time scales of the experiment. But there's really a variety of systems, of spin chains, of Fermi Hubbard models, or things like this. All those, I would argue many of the, if you want, prototypical models of quantum matter physics in one dimension end up being in that category. Okay. So, all right, so but the existence, all of those models are very well known, and they're kind of textbook models, and there are a lot of experiments, there are a lot of theory papers, so you may wonder why I'm telling you about these now. And so the reason is we now have a pretty good framework to understand the dynamics of those systems, which goes under the name of generalized hydrodynamics. And so the generalized just comes from the fact that you have all those conservation laws to take into account. And so this was introduced a few years ago in those papers, and by now this is a very well-established field. And I'm not really going to give you any technical detail of this. Like, the only message I'm going to convey is that it's basically everything that I told you at the beginning. That is, you take those systems and they have all those conservation laws, and you're just going to write down all those continuity equations and then express the currents in terms of the charges. And the surprise is, even though those systems have so many conservation laws, this is still a useful thing to do. So instead of having like a handful of hydrodynamic equations, like in Navier-Stokes, for example, you would have infinitely many for those systems. But even so, this turned out to be like a huge improvement over like solving the Schrödinger equation. Okay. Okay. So this, yeah, let me skip this. And so this allows you to like make quantitative predictions for the dynamics. And so I'm just going to show you briefly two examples, one from numerics and the other one from experiments, of how you can actually, of what type of predictions this can give you. So this is kind of an early example we had a few years ago with the Berkeley group. And so this is showing energy transport in like one of, this is a quantum spin chain. And what you're seeing here is some energy density versus space. And you prepare the initial states. This is kind of a funny initial state where you prepare like some bump of energy somewhere and you look at the way it spreads. So locally here you have some kind of higher temperature. So like the temperature is 10 units of J. This is in locally in thermal equilibrium, whereas here the temperature is 2. So quantitatively there's nothing like super exciting that's going on. You put some energy somewhere and you look at the way it spreads. Okay. The nice thing is, you can do this numerically exactly using a technique known as DMRG, but that's a technique that is super demanding numerically. So those curves ran for 2 weeks on a cluster, and there was no way we could go beyond time 20. This was kind of state of the art, how much you can do. The dashed lines are the predictions of this hydrodynamic theory. And it's also a numerical technique, so there's nothing, this is just solving things numerically. But the hydrodynamic equation are something you can run on a laptop in a few minutes. And of course, there was no reason to stop at time 20. We could go to very long times. So this has become, at least for all of those systems, like kind of a standard tools of simulating and understanding the dynamics. And so this has also motivated a new generation of experiments, both in spin chains, and that will be the second part of this talk, and like in Bose gases, where people really went back to try to understand and have ab initio prediction of dynamics, and really compare to this theory. And so let me focus on like the first experiment that was done in France. What you're seeing here is density. So this is a 1D Bose gas. You're seeing like a density of bosons. This is time. So the initial state is prepared in some kind of double well potential. So you have bosons trapped into like this double well potential. And at time 0, you kind of relax that potential and let the Bose gas expand in kind of a broader harmonic potential. And the solid lines are the prediction of this hydrodynamic theory, and the wiggles are the experimental measurements. Okay. And so it works beautifully well. I should say this is a purely, predictive theory. There's no fitting parameter of any kind. Okay. And I should really emphasize that, like, this is very hard to simulate. There are no good numerical tools, at least I know of, to simulate Bose gases otherwise. Okay. The nice thing as well is you could wonder, okay, maybe a 1D Bose gas you could simulate just using normal conventional hydrodynamics. Maybe conservation laws do not matter. You could could pretend it's just a normal gas, okay, and apply Navier-Stokes equations. And so those authors did this, so it's maybe hard to see it. So the dashed line known as GHD is conventional hydro. So this is your initial state. This is like time evolution. So the dashed line is the prediction of the conventional hydrodynamics. So what would happen if you ignore all those new conservation laws? Okay, and you see it's completely off. So the main message is you really need all those conservation laws to describe the dynamics of those systems. Okay, and this has been confirmed by different groups. So the second one is a more recent paper from Dave Weiss's group. Again, probing, they were looking at different distributions and things like this, but this has become really a quantitative theory to describe the dynamics of many body quantum systems. Okay. So here's just a brief summary so far. So the message is that hydrodynamics is a very powerful and universal theory, and it does not only apply to classical fluids, it even applies to theories that have infinitely many conserved quantities or nearly conserved quantities, right? So you could say your experiments will always have things that will make those things decay, but you have all those slow modes, and even if you have infinitely many of them, like this is still a very predictive theory. And it's a very universal formalism. You can apply the same formalism for classical and quantum systems. It applies to Bose gases, fermions, spin chains, and it's really a built-in formalism now in 1D to kind of understand the dynamics of systems that are close to those special points. Okay, so far at least, this is all really nice. This is kind of quantitative description of the dynamics. And I'm going to switch gears a little bit and tell you about something maybe more surprising that came along the way when thinking about all of this, which is the discovery of anomalies and anomalous transport in quantum spin chains. Yes?
So in the plot where you were comparing the conventional and generalized hydrodynamics,
Yeah.
do you really need all the conservation modes, or could it be that like you choose a few of them to get correct?
Yeah, no, that's a very good question. It's not something that people have done. It turns out it's actually easier to do infinitely many than just a few. So if you want, like doing 3 is kind of easy, but like doing systematically 4, 5, and so on would be quite of a pain. Whereas going straight to infinity is easier. It's kind of a weird thing, but yeah, it's a very good question. I would love to know the answer. I suspect that as far as the experiment is concerned, you probably don't need that many. You would probably need a handful more. It's pretty clear that you cannot ignore that you have those extra modes. How many you need is an open question. Yeah.
There's a natural ordering of them in complexity?
Yeah, they're kind of organized by locality, I guess. Yeah, some of them are, they're all extensive, but they all will have, yeah, if you're on the lattice, there will be like k-local things and growing. If for like a continuum model, like a Bose gas, they will have more derivatives and things like this. Yeah. Cool. Any other question? Yes?
Regarding the no fitting, so the transport coefficients are obtained by de-enlarging on some model and the downsides?
Right, and so here they're known because we know the thermodynamics exactly of those systems, so that would be by Bethe-Ansatz. So this is where the fact that they're exactly solvable comes in. So, the exact solution of those models apply to, we understand the thermodynamics of those systems, but up to very recently, anything related to dynamics would be very hard. And basically what hydrodynamics allows you to do is like bridge that steps. If you know the thermodynamics, you can, there's like some parameters that are known from other measurements, put that in, compute an equation of state from theory, and then you have your predictions. Great. Okay, so let me just, still thinking about a system that will have all those conservation laws and it will play a crucial role. Let me tell you about something that was more surprising, that was a big surprise to many people, and here again you'll see that it kind of generated some interesting interplay between theory and experiment. So going to talk about a superdiffusive spin transport. So it will be a very similar question or setting. So instead of thinking of Bose gases, we'll think of spin chains. So consider like this very simple looking Hamiltonian. So this is an Heisenberg quantum spin chain. So this is, again, not an exotic model in any way. This is a textbook model of quantum magnetism in 1D. Any solid state, textbook will probably have this Hamiltonian written somewhere. So not, this is a nice looking Hamiltonian interactions, and it will have conserved energy, and it has a spin rotation symmetry, right? And so it will have a conserved magnetization. So one question you can ask is about spin transport. So imagine your system is maybe coupled to some leads or reservoirs that have different magnetization, and you could look at a spin current. Or like maybe in linear response, an easier way to think about this is, just like I was doing, like put some energy bump and look at the way it spreads. Imagine you have some bump of spin, some excess magnetization. You could look at the way it's going to spread as a function of time. And in general, what you expect is the way this will spread will be as algebraic in time. And so this defines the so-called dynamical exponent z. So the natural expectation would be diffusion, that would be z equals 2. Okay. And so one of the surprises of recent years that came from Tomasz Prozen's group, that was numerical first, was that it looks like if you actually simulate this model, which again is not particularly exotic, it looks like spin transport is kind of very exotic and weird. And this is not specific to this model, I should say, but I will largely focus on this because it's a pretty natural model. So what they did numerically is they prepare an initial state with like a domain wall, where you have a domain wall of magnetization, and as a function of time, it will kind of melt, and you look at the way this melts, and it looks like the spreading goes with an exponent 2/3. So this is an exponent which is faster than diffusion. It would mean that any spin transport is faster than diffusion and slower than ballistic, if you want, okay? And this is weird because you would expect that in most systems, you would think that it would just be, here you don't have any momentum or anything like this. This is just a lattice. There's conservation of energy, magnetization. You expect everything should be kind of diffusive. And yet, they came up, at least numerically, with that exponent 3/2. So this came as a big surprise to many people. And the weird thing is, this was discovered relatively recently. This is a few years ago, but the thing is, this is a very well-known model. And you would think we know everything there is to know about this. There's a lot of it, it describes a lot of experiments on the solid state side or in cold atoms. This is not an exotic quantity in any way, just thinking about normal linear response transport. And this was missed by previous numerics. This was missed by previous theory, in particular like Luttinger liquids or field theories. And this was also mixed by experiments. So like neutron scattering and things like this missed this in this system. And it raised really interesting questions of like weird, universality classes of anomalous dynamics. So anomalous here means like non-diffusive or something like unexpected. And the surprise didn't really stop there. It turned out that spin transport ended up being related to some so-called universality class of a classical physics known as the Corda-Parisi-Zhang universality class, or KPZ for short. Okay. So this universality class before being a universality class, so this is an equation that was introduced to describe fluctuating interfaces in classical physics. And so this is a very well-known and ubiquitous equation in non-equilibrium classical systems. And it describes a variety of phenomena of like fluctuating interfaces in liquid crystals, so the way a coffee stain would kind of grow on a napkin, or the way fire interfaces, a fire would spread in a forest. Or like this is a windshield with some ice on it, and like, there's more like mathematical model. If you consider like a growth process where you have like blocks, sort of like Tetris, where you have like blocks falling down, but they kind of stick to each other, it will kind of grow patterns like this. And the way this interface kind of grows and fluctuates is described by this KPZ equation. Okay, and there have been numerous experiments on the classical side on liquid crystals and bacteria colonies and so on to kind of characterize, the way those interfaces fluctuate. And the surprise is that this physics somehow seems related to transport in that model, even though, of course, there's, they look very different. So what do I mean by this? So what you would naturally expect is like the hydrodynamic description of transport in those systems would be diffusion. Okay, so you have a magnetization, that's your conserved quantity, and you expect that Fick's law of diffusion would apply, so your current would just be gradient of m, and so any perturbation in spin would spread the square root of time, and it would have like, scaling functions that would be like a Gaussian in 1D. And so you can add noise if you want. So the noise should be inside the current here. Okay, so that's the so-called diffusion universality class, and that's why you learn about diffusion in your undergrad classes, and that's, diffusion is a thing, and it's really all over the place in nature. And if you have a single conserved quantity, that's the simplest hydrodynamic theory you could write down. In contrast, the so-called KPZ equation is very different. So this is an equation for this height field, so that describes this interface. And it looks superficially similar to that equation on the left, but it has like a nonlinear piece. And of course, this height is not really conserved. And so the claim is like magnetization is related to this height by this relation. Okay, so it's purely a numerical observation. And so this equation, if you solve it, both analytically or numerically, it not only spreads with a different exponent. Instead of square root time, it has that exponent 2/3. But it also has scaling functions. So just like diffusion would give you a Gaussian, this would give you a different type of function, which is not a Gaussian. Okay, and the same type. So again, the claim, and it's a purely empirical numerical observation, is that the same scaling functions and exponents that describe all those phenomena in classical physics end up showing up when you think of transport and hydrodynamics in those spin chains. Okay, and you know, and to this day, this is still like I'll summarize what we know on the theory side in a minute. But here again, it kind of inspired a new generation of experiments to kind of probe this. And both in solid state systems and also in more like engineered cold atom systems. So briefly, you can do this. So the first experiment I'm just quoting here is an actual solid state neutron scattering experiment. They're looking at a quasi 1D material. So this is a material which is well known in some range of temperature to be realizing this like Heisenberg physics. So at low temperature it would order, but in some range of temperature it's believed to be described by this Heisenberg spin chain. And so there was this relatively recent experiment where they claim, you see it has like this Carda-Parisi-Zheng in the title, where they claim to see, looking at like a structure factor that they measure in neutron scattering to observe that exponent. The thing is like, there were numerous experiments of that sort before. The difference is that they looked at a different regime. They're looking at relatively high temperature, which is, so it goes all the way to 300 Kelvin. So this is in a regime where hydrodynamics applies, okay? And they claim that they see something, it's hard to extract power laws on like this range, but they claim to see, there's one line which is ballistic, the other line is diffusion, and so the experimental data is in between. But you can also realize this physics in cold atoms. And it's actually in some way interesting that this wasn't done before. There were experiments in 2D Heisenberg chains, but not in 1D prior to this story. And so you can realize this physics, and you can realize this Heisenberg chain in a Bose-Hubbard model at large U, large strong interactions. And you pretty much in that experiment, you realize exactly what they did in numerics. You prepare a domain-wall initial state with more magnetization on the left and on the right. And you time evolve and you measure how much spin is flowing. Okay. And you do this many times and you can measure, so they call this polarization transfer as a function of time, which is how much spin has flown as a function of time, and they see that it collapses with that exponent 2/3. Okay. So by now this like phenomenon of relation to KPZ and like those exponents have been checked, by many groups, numerically, experimentally, and there are also some additional experiments I'm not quoting here, including some in preparation. Okay. So just to kind of wrap up this talk and give you an idea of like where we are, just thinking about those problems. So this, this relation between this, that physics is always interesting that way. You have like the same phenomenon or equation that ends up popping up in very different contexts. So to a large extent, this relation is not fully understood as I'm today, but we understand quite a few things. So, that exponent was observed numerically. This exponent 3/2 was observed numerically relatively early. So one thing we understood very quickly was that exponent 3/2 we understand pretty well. And the way we understand it is from this theory of generalized hydrodynamics that I told you about. Just staring at those equations and kind of counting, doing power counting if you want, we can see that exponent coming out. But this relation to this kind of KPZ equation remains a pretty big mystery. And one thing that kind of came out of the experiment is like even this relation between transport and like this KPZ equation ends up being more complicated than people had conjectured or appreciated, if you'd like. So the conjecture is like magnetization, like in that spin chain, is related to this kind of height function that describes like this interface that fluctuates by this derivative. And it's been, again, a conjecture that's, it's been checked in those experiments and in this numerics. But what people realized is that it seems like this is kind of true on average, if you want, but not for fluctuations. But what do I mean by this? And well, the way to describe this is actually easier to go back to the experiment. So what I'm showing here is like this cold atom setup. So this is imaging the spins down in your system. So what you see here is a bunch of 1D chains. They are decoupled. And this is the initial state, so they image here the spins down. So you see there's a lot of spins down here and not a lot over there. And they can also image the spins up. And so this is at time 0, and that's after some time t, where you see you have some spins down over here now. And so what you measure in the experiment, again, you let your system evolve, and then you image it. It's a quantum microscope, and in different chains, you'll have a different polarization transfer Q. And so in the conjecture is like this polarization transfer is related to something in terms of this height of this KPZ interface. The thing is, in the experiment, you not only have access to the average. If you then sum over many shots or realizations of your system, you can compute the average of this as a function of time, but you actually have a whole histogram, right? So you have a quantum distribution, if you want, of snapshots of this quantity. And that distribution, interestingly, appears to be kind of different from what you would expect from this KPZ equation. So in classical phenomena, you also have like a distribution, but those appear to differ. So if you want like this relation that people had conjectured, looks like it kind of works on average, but not for the full distribution. So in particular, like if you're in thermal equilibrium, if you don't have this domain wall, this distribution should be symmetric. So it's just saying like if you want, the charge can kind of flow to the right or to the left, but it should have no preference between left and right. And that's kind of clear. It's built in the physics of equilibrium systems. But this KPZ physics, it always has like a preferred direction. So like in those interfaces. And so this, thinking about this, I think was, as far as I know, at least for us, was really motivated by those experiments and the fact that you have not only access to the averages, but really the full distributions. So as we speak, and I'll just finish with this, we're basically trying to come up with good theories that would explain this. And again, it's really based on hydrodynamics, okay? And so over the years, we came up with kind of pictures of why you have superdiffusion in those systems. And it turns out to be due to kind of weird excitations or quasiparticles that we call Goldstone solitons. So, loosely speaking, they look like this picture. They look like Goldstone modes, which would be natural excitations in a low temperature ferromagnet. But in those systems, because of this weird feature of integrability, they also end up mattering for dynamics at high temperature. And once you have those excitations, you can write down a hydrodynamic theory of them. You don't need to look at those equations, but the claim is that those equations are basically the analog of the Navier-Stokes equations for this spin chain. So you have one equation for magnetization that looks like diffusion, but it also has like a velocity term which ends up being slow and has its own equation. Okay. Again, those parameters should be fixed from equilibrium. This is again a type of hydrodynamic theory, and the claim is that those equations reproduce this kind of KPZ behavior on average, but they're really a different universality class in that they have different fluctuations. And so this is my last slide, and so this is one thing that we're thinking about now is like understanding the not only like transport properties, but fluctuations, like looking at not only if you want the full probability distribution of the moments or cumulants, if you want, of like transport. And this is naturally something that at least on cold atoms, you would have access to experimentally. Okay. All right, and so with this, I'm just going to wrap up. Really one of the key messages is that hydrodynamics is a very powerful theory, even for systems with infinitely many conservation laws, which is something I think many people, at least if like in previously, prior to this development of generalized hydrodynamics, people always assumed that going beyond 2 or 3 conserved quantities would be, at some point, hydrodynamics would become useless. And so now we know that's very much not true. And, and there was some interesting surprises along the way. This discovery of this relation to KPZ is one of them. So I focused on this Heisenberg chain, but it's really a phenomenon that shows up in many different systems in 1D that have some non-abelian symmetry. And so there are many questions that, that we're thinking about. Thinking of distributions and snapshots and fluctuations is one of them. And, systematically breaking integrability, like we know all those conservation laws are not, they're broken in some way in the actual experiments, and yet you see all of that physics, and there's no good theory at this point to kind of interpolate between those two behaviors. And so yeah, with this, I will just thank you very much for your attention. Let me thank my collaborators. Thanks. Yes?
These Goldstone solitons, they're not topological solitons like in the sine order model, is that right?
Correct. They did just, yeah. That's right. They don't have any topological features to them. So the only key property, so the reason I call them Goldstone is they're kind of soft excitations, meaning they cost very little energy.
They're not as soft as magnons.
No, so yeah, they kind of bound state of many magnons, if you want. So they kind of, and this is kind of what's special about this model, right? So you can think of it as kind of a collective bound state of many magnons glued together that would normally be very unstable, but because of this special structure of this model, and it ends up being a very stable excitation, even at very high temperature. Even if the ground state is actually not a ferromagnet, if you're in the antiferromagnetic regime, this is still a good excitation for your system. Okay, so there's part of this physics is sort of counterintuitive, and it comes from this special feature of integrability of this model.
You mentioned that you end up getting like very large number of conservation laws in this particular 1D system.
Yep.
I'm wondering in what sense they manifest, because it seems to me at least you're able to, I guess obviously you've given a sort of very broad overview, but it seems to me you're able to describe your physics in just one sort of non-Stokes equation that's modified. I'm wondering how the effect of many of them at the same time.
Yeah, you mean in that specific example, or like going back? Yeah. So yeah, here there's something sort of interesting in that case. So like when I talked about Bose gases, you really need infinitely many equations, and you need to solve all of them. Even if you care only about density of bosons, you need all of the all the equations to kind of solve, to understand the physics. This is kind of a more special case, because you notice that I only have two equations here. And yeah, there's some kind of magical decoupling in this problem that's, yeah, there's like a decoupling of all the other conserved quantities kind of decouple, and you only have a handful of equations. But still, that one extra equation, so normally if you didn't have this term here, this would be a diffusion equation. So you only have one extra conserved quantity, which is basically like a velocity for this magnetization. So you have one extra slow mode, but that slow mode is like super important, and it completely changes the physics. And instead of giving you diffusion, it gives you this completely new universality class. So you're right that this is kind of special. You don't need this full hierarchy of infinitely many conserved quantities here. You just need one.
Are there other problems where you can only get these two conserved quantities without the infinite hierarchy?
Yeah, I don't know. That would be very interesting. Like I'm not sure. So basically, this quantity is related to energy current, like in this system, and so this is kind of a Carroll quantity. Like this is like a velocity, so it's odd on the inversion. My experience is that if you impose energy current conservation on the lattice system, you will basically enforce integrability. Like so, imposing this one conservation law will generically give you a whole structure. But in principle, it need not be the case. And it would be very interesting if that were true.
I wonder whether integrability here is important. Like if I add a near neighbor term,
Yeah.
screws up the integrability.
Yeah. Yeah, so that's a good question, and it's not something I really talked about too much. And the claim is this is actually extremely stable. So we think integrability matters in that it's probably underlying the physics, but this phenomenon of like this relation to KPZ and superdiffusion, so you can the steady state experiment, there's a lot more things going on than just this Heisenberg physics, right? At 300 Kelvin, you probably have, you have phonons, you have lots of things going on, and yet you still see something. the cold atom experiment is very clean, but it also has a lot more things going on. So, we don't have a good theory of it yet, but we have a lot of evidence numerically and also partly from theory that this is a lot more stable than what you might naively expect. So if you add a next nearest neighbor interaction, for example, you still see that exponent for very long time scales, for as long as you can simulate, basically. You never really see diffusion. And this is still a mystery in some way. We don't really understand why.
Another question, like you mentioned that there are field theory calculations which miss this static lab. I mean, like one field theory that I can think of is following like the collaborative Cardi quantum protocol, where you have some boundary condition chain operators that they time evolution.
Yeah. So if you do like a CFT calculation, you will really miss this. So it would be like a Luttinger liquid ground state here. So yeah, so it would give you basically field theory calculation would give you you would get ballistic transport, right? If you have a conformal field theory, you would get something trading ballistically. And if you put like dissipation, if you put like a mechanism to relax this, you'll get diffusion, but nothing in between. So any type of field theory calculation missed that, at least that I know of.
Do you have a understanding why?
Well, because it doesn't know about this one slow mode that I said. Like it doesn't, when you go to the field theory limit, you kind of forget about the microscopics, and what we know now is there's one like additional slow mode that is very important and you need to take into account. And if you kind of forget it once you coarse grain and go to the field theory, you'll miss this.
Great. No other questions? Let's thank Romain again.
Thanks.
Very nice. It makes a very nice glow print.